Screen share going. Screen 2. Okay. Hopefully you guys can see this. Can somebody just let me know if you can't see it? Okay, I'm assuming that means everyone's good. Okay, so I want to talk about dimensionality reduction today. I'm going to be doing an unusual amount of gesturing and finger. Thanks, Alex. I'm going to be doing an unusual amount of hand gesturing because the two things that I want to talk about, the two dimensionality reduction algorithms I want to talk about today, are PCA and t-SNE, and both require, let's say, a little bit of fiddling around. So, so anyway, make sure, I guess, that your setup is such that you can also see my hands from time to time because they'll be popping up. But before we dive into dimensionality reduction, I wanted to kind of make a quick philosophical note about dimensionality reduction. There's an understanding most people have that when we talk about dimensionality reduction, we're really talking about two different things, either some kind of PCA or some kind of t-SNE. That those are the two so-called dimensionality reduction techniques that exist. At a high level, dimensionality reduction is the idea of taking something that's high dimensional. So, for example, a description, like a row that describes, like, I don't know, a user or a person. You might have age, height, weight, gender, income, like a whole bunch of really, like a very high dimensional data, lots of dimensions, lots of features, in other words. And taking that input and then basically finding an intelligent way to compress that, to represent it as a shorter object, one with less. Oh, it sounds like somebody's. Nadim, it sounds like maybe there's clanking of food there. Do you mind if I just mute you? Oh, thanks. Feel free to unmute yourself if you have questions too. So, yeah, at a high level, it's just this idea of taking something that's very high dimensional and then converting it into something that is low dimensional. Now, most people think that dimensionality reduction is like for visualization predominantly. So the idea here is, if I describe a person and I give you 15 different features, we talked about age, height, weight, gender, income, so on and so forth. So you have 15 features. Obviously, you can't plot a 15-dimensional thing. You can't make a plot of that and then just show it off to a CEO or a team lead or whatever. So what a lot of people use dimensionality reduction for is to take that 15-dimensional thing and convert it down to 2D, so then you can plot it. And you can somehow show clusters of people who have similar ages, incomes, and so on a plot, right? So that's the dream. That's one of the use cases for this. But what I want to point out is that all machine learning is actually dimensionality reduction. So there's nothing actually special about PCA or t-SNE that sets them apart from all the other machine learning algorithms. In reality, every time you do machine learning, let's say you're trying to predict the athleticism of someone based on their height, weight, and so on, right? So you're taking this high-dimensional input, this athlete description with like 15 different features, and then you're converting that into a prediction about, let's say, the athleticism of that person, maybe how many goals they'll score in a hockey game or something, right? So you're going from a high-dimensional thing to a low-dimensional thing. You're from this description of a player to a prediction, a single number that tells you something about that player. That's dimensionality reduction. And it's also dimensionality reduction when you do a classification task rather than a regression task. All machine learning fundamentally works the same way. In every case, you're taking a high-dimensional input and you're turning it into a lower-dimensional output. Okay, so I really have come to look at the term dimensionality reduction as a real misnomer. It's not that it's this special that t-SNE and PCA are special in that they reduce dimensionality. They're just different in the sense that they're unusually flexible with respect to the dimensionality of the outputs. So what do I mean by that? Well, in a standard machine learning model, you're either doing, let's say, classification or regression. What you do is you go from this high dimensional input, again, let's imagine 15 dimensions or whatever that describe a hockey player or something, and then you're going to a one-dimensional output. Okay, so that mapping is, we do it so much that we often don't think about what we're doing to the dimensions, but that's really what we're doing. One way of looking at machine learning is as this process that takes you from high dimensional to low dimensional outputs. Most of the time it's one-dimensional outputs, but some algorithms are more flexible than that. Some algorithms can give you an output that is two-dimensional or three-dimensional or five-dimensional. And that's exactly what the two algorithms we'll be talking about today can do, PCA and t-SNE. So I'm going to start with PCA. It's Principal Components Analysis. That's sort of what that term is. And I think most people here have probably heard about it. I think most of you probably know roughly how it works. But my hope today is to give a little bit of a deeper picture, more intuition about how PCA works, why it works, and maybe to frame it to you in a way that would make it easier for you to explain it as well during an interview or something like that. And so what I'm going to be doing, actually, sorry, before I dive into that, I want to pause first. Does anybody have any questions about that preamble? Because I know it's maybe an unusual way of talking or thinking about dimensionality reduction or machine learning. Okay. All right, I'll assume everything's good. Just going to check the chat, actually. Okay, yeah, thanks, Alec. Great. Okay, so we're talking about a particular kind of dimensionality reduction technique that's going to allow us to go from a high-dimensional representation. Let's imagine that. Let's imagine, again, we'll use this athletics example just because that keeps popping for whatever reason at the top of my mind. But let's imagine we've got a bunch of hockey players, okay? And there are 15 dimensions. We have 15 columns, in other words, 15 features that we're looking at. We have like skate sharpness and length of stick and number of minutes on the ice and so on and so forth. Huge number of these features. And what we'd like to know is, are there commonalities that the players who, let's say, get paid really well or score a lot of goals tend to have, right? Are there clusters, maybe, we might say, in our data? That's one thing we might be curious about. You can't plot 15 dimensions. And so somehow, if we want to do a clustering analysis on this kind of stuff that we can visualize in 2D, so if we want to just do a qualitative kind of visualization, we want to reduce that dimensionality from 15 dimensions down to 2 dimensions, maybe 3 dimensions if we feel comfortable rotating a 3D plot, but more realistically down to 2D. So that's what PCA is going to do. It's going to allow us to take that 15 dimensions, turn it into 2 in a way that preserves as much of the information in those points, in those distributions as possible. And we'll talk a little bit about what that means, what that information is and where it's hiding. And so this is where I'm going to start with my props here, and maybe I'll have to be able to see myself here for the first little bit anyway. Sorry, this is going to seem very egotistical, but I'm making myself front and center here just so that I can make sure that my hands are visible. Okay, good. So here's my hand. Nothing too special. We're going to imagine that every single one of my fingers is a point. And specifically, it's going to be a point in 3-dimensional space, right? Because there we go, 3D. Cool. So these are points that we could imagine representing a different player in some sport. Okay, so we'll imagine each of these is, let's switch sports and talk about basketball maybe. So we'll say these are all 5, these are basketball players. And, well, we have 3 dimensions that these points live in, which means we have 3 features. So let's imagine that we have height, we have weight, and then, whoop, that was really intense, and then we have, I don't know, arm span. Okay, so height, weight, arm span, right? And these points, they all live in that space. Okay. So this might look like it's a 3-dimensional problem. It might look like these points are, that we can only represent these points in 3 dimensions. Sorry, I missed that, Jeremy. Do you mind unpacking that? Sorry, I want to make sure that, am I moving too fast here?
We can see you much better by pinning you on the screen. Yeah.
Oh, okay, sweet. Okay, thanks. Yeah, good tip. Sorry. Okay, yeah. So we have these 5 basketball players, and they all have, you know, a value of whatever it was, a value of, you know, height, weight, and arm span, or whatever the axes were, right? Okay, so these points live in that 3-dimensional space, and so we look at this, we're like, okay, that's a 3D problem, right? Our intuition says, you know, this is a 3-dimensional problem, no question. These points, to describe them fully, I need 3 dimensions. But that might actually not be the case, Because what you might notice is that these points all live, conspiratorially, I set up my points, my fingers this way, they all live on a plane. Which means if I can just change my perspective, if instead I rotate my points so the plane is facing you, now we have a two-dimensional problem. Okay, so initially we had these 5 points, 5 players, living in three-dimensional space, and we look at it, we're like, yeah, that's a 3D problem, until we realize that actually, look at that, they're sitting on this plane, so if I just like change my perspective to look this way, like that, now I have a 2D problem. So this was actually a two-dimensional problem hiding in a three-dimensional space this whole time. Right? So what we've just done is we've basically reduced the dimensionality by doing that rotation. We just said, okay, you know what? I don't actually need that many degrees of freedom to describe the system. So that's the sort of intuition behind how PCA works. Now, it turns out, of course, not all 5 points that you'll find in nature will actually fall on a plane. That was actually really conspiratorial. I was lucky that it worked out that way, and I did this deliberately. In reality, sometimes you'll have a situation like this. So one of the points here is just off the plane slightly, right? So the thing is, that's maybe a sacrifice we're willing to make. We're maybe willing to say, okay, yeah, I know that one of these points is a little bit off the plane. Maybe a second one might be a little bit into the plane. They're not perfect, but surely I still get some value from changing my perspective this way and looking at it like this. I'm sacrificing this depth information here, but maybe if that depth information isn't too big, then I'm not sacrificing all that much, and in exchange, I get to take a complex problem and turn it into a simple one. So that's that trade-off. Let's look back here at the plane, at this PCA kind of plane that we're identifying here. Okay, so we have 1 point that lives off the plane. The plane is almost, you can think of it as almost like an average, right? It's like the average position of all these points, right? This plane represents where on average these points are. If you had to come up with one plane, you kind of fit it, you go, where's that gonna go? I mean, on average, it's about like that, right? Or maybe something like this, okay? So this point that lives off the plane is actually kind of like, you can think of it as like a spread away from the average, right? So it's slightly different from the mean value, the average value of these points, of these other points in the family that are closer to the plane. So there's a way.
Could we call it an outlier?
Well, okay, yeah. I mean, yeah. If it was dramatic enough, we could. You're right. Yeah. Let's pretend it's not. Let's pretend it's pretty close. Okay. That's a good point, but let's pretend it's pretty close. So we have all of our points actually could kind of be slightly spread right around that midpoint, and the plane really represents just the average point, the average location of those 5 points. It's like a compromise, right? So this plane roughly represents, it's the closest we can come to putting them on a 2D surface. Now here's the thing. This point is a little bit off that plane, and we have a word for spread in statistics. That word, actually we have a lot of different words for spread in statistics, but one of those words is variance. Right? We also have standard deviation, right? Same idea. But basically the spread of these points around this kind of like average position of all those points, which is this plane, the spread of those points we can think of as a kind of variance. Right? Now that variance is exactly what we're losing when we lower the dimensions to 2. Right? We start off here and we have all this beautiful spread around the average position, but then when I change my perspective and I rotate to look at it this way, I lose all that. It flattens out. See? All that nice little spread gets pancaked out, and we get this, right? Now, the hope, of course, is that there isn't that much spread, right? We're not, like this would be really, like, I mean, that wouldn't be very helpful. If you just had a complete random jumble of points, you're going to lose a ton of information, and that's really bad, right? So let's imagine that that's not the case, and instead, we just have like a couple of points that are a little off that plane, right? So we're going to lose that. We're going to lose that spread about the mean. We're going to lose that variance. And that's the cost. That's the price you're going to pay in PCA every time you reduce the dimensionality in that way, right? We're losing that depth information. We're losing that spread. Whoops, sorry. We're losing that spread about the mean. We're losing that variance. And this is a number that people use in PCA when they talk about the amount of information that you sacrifice by going from high dimensions to low dimensions. They refer to the sort of amount of variance that you lose as the explained variance. Okay, but that's the kind of keyword you want to use. So this spread that gets crushed out when we reduce to just a two-dimensional problem here is the explained variance that we lose. Okay, here's the thing. We're not done though, because we could actually, from here, I wish I had a pen. You know what, we'll just use this. I have a fork, but that's, oh, I know I have my cell phone. That's what I'll use. Okay, so we started off here, right? We projected onto a surface like that. We got a two-dimensional problem. And now, let's imagine my thumb's over here. And now we can actually reduce the dimensionality again. We can go down to one dimension. And the way we would do that is by fitting a line this time rather than a plane. And then, boom, we're gonna collapse those points to that line, and we end up there. Okay. So we've moved from this three-dimensional problem down to a two-dimensional problem, down to a one-dimensional problem. And each time we do that, you'll notice, like at first, right, the amount of information I'm losing is pretty small. I'm just sacrificing like, 1 point, a little bit of spread, right, to get here. But then when I want to go from two dimensions to one dimension, I'm losing all that spread. That's a lot more. Finally, if I go from one dimension to 0 dimensions, which is just collapsing everything just to a point, boom, I lose even more. So the explained variance that you lose increases with every step of your PCA. Every time you reduce your dimensionality by another dimension, you basically lose even more information than you lost with the last step. Okay, so essentially this is what PCA is doing, is it allows you to start from a high dimensional problem and then kind of like look at what's the angle that I can look at my data from that's going to make it closest to being an n-1 dimensional problem. So if it looks like a 3D problem, what's the perspective I can take that's going to make it look the most like a two-dimensional problem? And then if it's a two-dimensional problem, what is the perspective, the line, in other words, that I can draw that's going to allow me to see that as a one-dimensional problem, and so on. Okay. So every time you do that PCA, you lose more information at every time a dimension is sacrificed. And ultimately, you get down to 0 dimensions, and you've lost all the data, the information that was in those points. So we can quantify the information that we lose as a variance. Like I can actually slap a number onto the amount of information there is in this distribution of points because it's the sum total of all the variance that I lose as I collapse from 3 dimensions in this case down to 2 dimensions, from 2 dimensions down to 1 dimension, from 1 dimension down to 0 dimensions. If you add up the spread of those points about the thing that you're collapsing it to, in each case, that's going to add up in total to the total amount of variance that was in your data. In other words, the total amount of information that your data contain. Does that make sense? Are there any questions about this? Pick on some people here. Okay, cool. Awesome. I'm glad it worked, Jeremy. Gordon, I'll pick on you just because. Does this make sense? Do you have any questions about this? Okay, sweet. All right, I'll pick on one more person. Sayin?
Yep.
Sweet. All right.
Makes sense, yeah.
Cool. Okay. If it doesn't make sense to you and you feel pressured because other people say it makes sense to you, feel free to send me a message on Slack because I know this can get very abstract. Okay, that's PCA in a nutshell. That's how PCA works. And that's why when you use scikit-learn, you'll run into, when you use PCA in scikit-learn, I should say, there's this quantity called the explained variance ratio. And the explained variance ratio is the fraction of all that juicy variance that you lose. Let's look at going from, what would this be? 1 dimension down to 0 dimensions, right? So this is telling us how much information was contained in that first dimension, right? How much variance, how much spread about the average position here, right? So if you add up all those distances together, right, that gives you the explained variance that was contained in the first principal component. That is only a fraction of the total variance that was contained if you added together this to this to this. Sorry about the sound effects, guys. That's gross. Anyway, the point is, if you added together all those variances, right, you get some number. That number would be big. And each time you do this, you're only getting a fraction of that total amount of variance. And that fraction is what's called the explained variance ratio. It's the ratio of the explained variance in total in your data set that was accounted for in just that one dimension that you just squashed. How is the reduction in variance? Oh, yeah, calculated. So, good question. So Jeremie was asking, and hopefully I'm not misinterpreting, but he's asking, how do you calculate like the loss of variance for each of these things, right? So the short answer is, and I'll give it to you intuitively, and we can get into the math later if you're interested, but I think the intuition gets you 90% of the way there. So the idea here, for example, if we look at when we go from 3 dimensions down to 2 dimensions, and we're going to imagine we're just sacrificing just this little guy. So this guy has a certain distance. I wish I had a third hand, but he has a certain distance from that plane, right? That distance, that depth that we're losing here, that quantifies that variance, right? So there's a sense in which if if this guy's off a little bit and maybe this guy's off a little bit, so if I add this to this, if I add those two distances together, 1 and 2, that's going to give me the total amount of variance that I just squashed when I pancaked this out to do that. Does that make sense, Jeremie? I don't seem to be able to hear you right now. Sorry, Jeremie. You can write it in if that's helpful. Yep, no worries. No pressure. Okay. Okay. While Jeremie writes that up. Okay, yeah, sounds good. I was gonna say, yeah, feel free to chime in later. Okay, good. So, yeah, very high level. That's how that works. I want to show you guys a. Oh yeah, I didn't even tell you how this can all go horribly, horribly wrong. Before I do, let's look at this. So, here's the picture that I was literally hand waving about a second ago. So for PCA, right? What are we going to do? How are we going to do this? Yes, okay. Ignore the squiggly line at the top here and instead focus on these bars. Okay. These bars correspond to the amount of variance in each dimension. So in this case, I mean, I guess this is like a 14 or 13 dimensional problem that they're looking at. So I can't show you how you would go from dimension number 13 down to dimension number 12, and then from 12 to 11, and 11 to 10, and so on. But what I showed you was the next best thing, which is how you go from 3 to 2, from 2 to 1, from 1 to 0, right? So PCA is doing something in these higher dimensions that's analogous to this process of finding the right perspective and squashing, and then finding the right perspective and squashing, and then finding the right perspective and squashing. Okay, so something like that is what PCA is doing at these higher dimensions. And here you're plotting the amount of squashing that went on in each dimension. In other words, the amount of information, the amount of variance that was contained in each dimension. So, this suggests that this, the third dimension here was clearly, pretty big step up to the second dimension, and then you're losing a ton of information when you go and squash it down to one dimension here. So there's one cool statement that you can make about PCA, or when you use PCA to solve a problem like this. So here you can clearly see, like, we have it's a 13-dimensional data set, but you can see that the vast majority of the information is actually just contained in, like, you can squeeze it into like 3 dimensions, maybe 5, but pretty much, I mean, you put it in 3 dimensions and you're getting a vast majority of that data or of that information. And so what PCA lets you do when you plot this out, when you look at this is the explained variance ratio for each dimension. And what this allows you to say is something like, well, you know what? Although the company or the client or the customer gave me 13 dimensions of data, this is actually secretly like pretty much it's a three-dimensional problem hiding in 13 dimensions. The reason that you're able to say that is that by sacrificing like, what is that, 10 dimensions that you're cutting out, you're barely losing that much information. Like you still have the vast majority of the information in the data set that's confined to those 3 dimensions. So this actually tells you like, yeah, it's actually a 3-dimensional problem, more or less, up to a certain point. It's about a 3-dimensional problem. And what you can see, so these bars are the individual explained variance. The cumulative explained variance is the sum of what you get from the first dimension, and then you add the second dimension, so it increases up here. So what this is saying is like there's about roughly 60% or so, maybe about 57%, 58% of the data, of the information in the data set is contained in those first 2 dimensions, right? And then we add that third dimension, and then we can go up to about 75% or so, and so on and so forth. So 70 to 75% of the information is contained in just 3 dimensions. And that's a very powerful thing to be able to say with PCA. That's a really, you've compressed your problem down significantly at that point, and that has a lot of value. It has value for storage, right? It means you're able to store your data set more cheaply, and it has implications for interpretability that we'll explore in just a second. Does anyone have questions about this so far?
Hey, Jeremy, I have a question. So it looks like according to that chart, when you go from, let's say, 13 to 12 dimensions, you pretty much retain everything or close to everything. Is it more so that each of the 13 dimensions are transformed slightly when you get to 12 dimensions, or is it more so that there's, let's say, 2 dimensions that are really highly correlated and those are smushed into one and the rest of them are kind of not really affected too much? Does that question make sense?
I think it does, and actually maybe some of these slides will be helpful in answering it. So keep me accountable, because I want to make sure I scratched the itch, let's say.
Okay, thank you.
No problem. Here's my attempt to answer Alex's question. So here's essentially what PCA is going to end up doing. We have a 2-dimensional data set here, right? And this would be the process of squashing this 2-dimensional data set down to 1 dimension. So the equivalent, if you look at my hands now, of doing something like like this, right? We have some spread in 2D space, and then we go, oh, you know what? These points, they all kind of seem to live roughly on a line. And I can actually squash them down to that, and then I have like, all my points on a single line. So that line is, let me just rip that out. That line is something like this, right? So something like that, right? It seems like these points are roughly living on that line. And so what I'm then doing is I'm saying, all right, well, let me then pretend that this line is like a new feature. And it's the only feature I'm going to keep track of. Where these points live on this line, so for example, this point here has a value of 0 along this line. And then this point here has the highest value of all the points along this line. If you kind of imagine that this is like a new x-axis, right? So each of these points has, in this direction, an increasing value along this new invented axis that we've created. This is a new feature. It's an entirely new feature, and it's a weird new feature because it combines height and weight together. So when you ask me what's this feature, what does it represent? I don't know. I mean, it looks like it's about, because the slope seems to be almost equal to 1, it's about a 50-50 mix of height and weight. It blends those two together. And for whatever reason, that actually is it seems to be the best axis that allows us to lose the least information when we then kind of scrunch this down to 1 dimension. So what's happening every time you reduce the dimensionality is you're actually kind of blending all your features, your fundamental features, together to create these weird new features that are not just height, not just weight, not just age, not just income, but some weird combination like 0.1 times height plus 0.3 times weight plus 0.6 times something else. Those new combined features are what these they're like what this plane represents, right? This plane it's not perfectly aligned with any of my fundamental axes, right? So it's some weird mix of those three features. And so that's the weird thing about PCA. What you get at the end of the day is like you get the privilege of being able to look at your data in a lower dimension and actually plot it, and that's great. But the price you pay is that your axes become a weird mix of these fundamental parameters that you'd like to be able to say, oh well, it's just that more athletic people have higher weight or they have a higher height, but in reality, the statements you'll end up with are things like, well, no, the best athletes seem to be the ones where 0.2 times height minus 1.4 times weight is higher, right? Something like that. So hopefully that makes sense. Alex, did that address your question?
Yeah, that did. I do have a follow-up though, if that's all right.
Yeah, of course.
Yeah, so would it be safe to say that you would, I guess, retain the most amount of variance the closer that those points are to the new projected line?
Correct.
Okay. And then would it also be safe to say that if this black line was horizontal, meaning like let's say height didn't really change too much, um, would that also be safe to say that you would be retaining more variance in that scenario as well?
So do you mean if it was like something like this?
Yeah.
So actually what happens in this case is kind of interesting. So in this case, the variance that you lose is going to be the same, right? Because the variance is the average. It's something like the average distance or the total distance of all these points from that new axis, that new line, or that new plane that you have to define, right?
Hmm.
So rotating this doesn't change that sum.
Mm.
But what does happen is if this line is basically horizontal, which I'm doing a really bad job with this. Sorry, this is brutal. Okay, something like this. If this line is horizontal, what it means is that, well, it kind of looks like weight is the only parameter that matters, right? Because like height, there's not much information in height. Pretty much all the interesting spread is happening along the weight axis. And so this principal component, this new axis, I mean, it ends up just being the weight axis. So this is a special case where you actually can say things like, yep, it seems like weight is the thing that matters, whereas in this case, it's a 50-50 mix, roughly speaking, of both. I hope that made some amount of sense here.
Yeah, that makes sense. Thank you.
Okay, yeah, no problem. Yeah, hopefully this is helping with building intuition. I think everybody has a different way of picturing these things, so anyway, hopefully this is a useful one. I want to show a failure mode as well of PCA, a way it can go really, really badly wrong. And that is, actually, first I want to undo all my changes here because I did have, there we go. Okay, let's take a look at this. Okay. Can anybody hazard a guess as to why this would pose a problem to PCA? Why we might get like wonky results? Just gonna pick on someone for kicks here. Gorang?
Hi.
Hey.
I think because there are two different clusters, uh, the distance is different for each cluster from the plane or whatever that dimension that we reduced to. It's
Yeah.
not basically comparable, I guess.
Yeah, you're bang on. I mean, there's a sense in which you look at this and you're kind of like, well, what do I want PCA to do? I want PCA to reduce the dimensionality in a way that will preserve the interesting features of this of this distribution of points. Now, what's actually going to happen here if we run PCA is we're going to try to pick which axis we want to scrunch our points to, and like, let me just grab this guy here. All right, so for this distribution, we kind of feel like, okay, this is the right axis, and it's the same axis for this one. But when you put these two together, if you really want to minimize the distance of the points from that new axis, you're going to actually end up with something like this, right? Because there's way more distance between these clusters than the distance between those points and that line that we're fitting. So this is a failure mode of PCA. It's something to look out for and be aware of, that you will lose some of the sort of you'll be sacrificing stuff like this from time to time. And the way to tell if this is going on is if you see a big jump in, like, from here to here, for example. It seems like you're sacrificing a lot of information. Well, that's what's going to happen here, because basically this line is not well adapted to either of these shapes at all. And so we're just sacrificing like a ton, like every point is way, way, way off that line. That's no good, right? Does somebody have a question? I think I heard somebody unmute themselves.
Yes, I did. I didn't catch where you are pointing with your mouse from if you see a big jump, like, for example, from here to here.
Yeah, great question. So, I mean, here I'm just picking the biggest one that sorry, this is a little silly because obviously the biggest jump will always be from 2 dimensions to 1, but it seems like this is a very significant increase in the loss of explained variance. I hope that makes sense.
Yep.
Okay. So basically you're looking for like something like, like every, the explained variance is really like pretty nice and high, and then all of a sudden at dimension 4 or 6 or whatever, it just crashes. And if you see that, then that's a red flag that actually, you know what, I probably did have multiple clusters going on or something, and basically my PCA is now really starting to oversimplify and sacrifice a lot of that information that I should want to preserve. Cool. Okay, that's PCA in a nutshell. PCA is great because it allows you to at least know what the axes are that you're generating at the end of the day. At least, even though they're weird, right? It's like some weird combination of height and weight. It's, maybe this is 0.5 times height plus 0.5 times weight or something. And like, sure, I'll give it to you. That's a weird feature, but at least you know what it's made of. At least you can speak about that axis as being really important. And if someone asks you, like, what are the most important features of this distribution, then what you can do is you can say, well, let me take a look at the first principal component, right? The most important principal component here, and I'll take a look at how it's broken down, what it's composed of. And in scikit-learn, you can actually do that. You can sort of crack open your principal component and look inside, and what's the balance of height and weight and so on. And that'll give you a bit of an intuition, at least, for what features are important, right? If certain features keep showing up in the early principal components, like 1, 2, 3, and 4, then those are probably reasonably important features. So this is one way of looking at feature importance with PCA. However, PCA has a problem. And the problem that PCA has is that it's a linear transformation. So it's very good at capturing linear relationships like this. But suppose instead that we had something that looked more like, okay, I'm going to doodle on the spot. This is not going to go well, but this is going to be a real mess. All right, okay, let's start with a couple more points. Something that looked more like, okay, like this. This is a non-linear a nonlinear correlation, right, between our x and y axes. And the problem with PCA is that it's not designed to handle nonlinear correlations. I'm going to make it even more obvious, maybe, like this. And yet nobody would look at this distribution and say that there isn't an interesting pattern going on here that we would probably want to catch and notice, right? Like there's clearly some, like there's some machine learning algorithm that we should be able to run to catch this. But it's not going to be linear. And PCA is not going to be able to, with a straight line, right? Because that's what PCA can do. We pick a straight line and we kind of try to, like, we'll end up with something like this, and it's going to be really nasty and gross, and it's going to go terribly for us. Okay, so we don't want that. So PCA will generally fail at doing, let's say, a good job of dimensionality reducing stuff like this. Even though, and I want to really emphasize this is still a one-dimensional problem hiding in 2D space. Why? Well, because if I had a J-shaped line that was still a one-dimensional line, but I just ran it right through this thing, that would still be a pretty good approximation for like where all these points are, right? So it is still a one-dimensional problem, or it's something like a one-dimensional problem, right? These points are roughly along, I'm trying to make it a little more obvious that they're, roughly along, spread about a particular line, right? It's just that that line isn't straight, and PCA can only draw straight lines. So it would be great if we had another algorithm, a different one, that was able to reduce the dimension down to, from 15 dimensions down to something we can plot like 2D, but that could capture these nonlinearities. And that algorithm is called t-SNE. It stands for t-stochastic neighbor embedding. You can look it up after. The mechanism for t-SNE, it's going to require a little bit more hand waving, so I'm going to switch. By the way, sorry, is this clear? Does everybody understand that point that I was making about the straightness of the lines with PCA and the fact that this is still a one-dimensional problem, basically?
Yeah, it makes sense.
Okay. All right, Alex, I'm assuming that you've spoken. Oh, sorry, yes.
I have a question. So if you draw a line along these points, I mean, using PCA, I wouldn't be able to capture the idea of the points. I couldn't get it why PCA would fail over here.
Right. Okay. So PCA, as we see here, PCA is only capable of drawing straight lines, right? Or for example, like in the case of the 3D sort of hand waving thing that I was doing, PCA was a plane, right? We mapped our points onto a plane. It's basically like a plane is like a straight line, but in higher dimensions, right? Now, that plane is kind of straight. It's a rigid, straight plane. It's not this curvy, it's not like, I've got a rag here. It's not like a weird shape like this or whatever that can accommodate like weird nonlinear curvature in my hand structure here, right? So this plane is actually very constrained, just like this line is, to only catch certain kinds of correlations. So, for example, if my fingers in 3D happen to actually be arranged like in a bowl shape, I don't know. This is going to go really badly. Anyway, if my fingers secretly, if the shape that they were mapping out was like a bowl, then this would fail miserably, right? I just wouldn't be able to capture that. And in just the same way, the PCA works great on data sets that are distributed as if they're falling on a straight line. But the moment they fall on a curve, imagine squishing this curve down to, the best line I think I could draw would be something like that, right? And now that's not the worst, but I'm obviously sacrificing a lot of like the distance between those points and that line is a lot bigger than it needs to be, right? Does that make sense?
Yeah, it does make sense. Yeah.
Okay,
Thank you.
sweet. Yeah, no problem. So yeah, what we'd want is an algorithm that's able to reduce this down to one dimension without being limited to just straight lines. And that is t-SNE. So the way t-SNE is going to work, and I'm going to go back here to sorry, bring myself up. Oh, there we go. Okay. So the way t-SNE is going to work is we're going to look at pairs of points. Instead of saying, okay, we want to like project this onto a plane or something, we're going to say, okay, let's look at, let's call this point number 1 and point number 2. Okay, and we're gonna identify every pair of points that we can possibly identify. And what t-SNE is going to do is it's going to use the following intuition. Points that are close together in 3-dimensional space should also be close together in 2-dimensional space. So what we want to do is reduce the dimensionality in such a way as to make sure that points that are nearby, pairs of points that are close together in 2D are also close in 3D are also close together in 2D. Or points that are close together in like 50 dimensions or 15 dimensions are close together in 2D as well. And so what we're going to do is we're going to try to say something like, okay, the criterion is points 1 and 2. Let's say these two are really close, and then we'll do something like that. What we would hope is that if the points look like this in 3D space, that in 2D they're also close together, and then these guys are also far apart. Right? So in essence, what we're trying to do is preserve the distance between points as we reduce the dimensionality. That's roughly speaking what t-SNE is doing. It actually involves a whole bunch of deep learning, neural network stuff in the background that you do not need to worry about. But the bottom line is that that's sort of how it works. And because all it cares about is the distance between those points, essentially that has the effect of meaning that there's no unnecessary constraint about like having flat geometries or straight lines that PCA imposes, so that now you can actually capture those interesting shapes. Like say this one here. However, the cost of that is that you can no longer tell or interpret what those new axes are that you've just created, because they're no longer like a linear mix of like height plus weight or whatever. They're totally different. In fact, the rule that applies to a nearby pair of points here might not apply to a different pair of points because, because neural networks. It doesn't really matter. But the bottom line is that this is a much less interpretable way of doing things that tends to give you more, let's say, semantically correct clusters at the end of the day, because it accounts for nonlinearities, because it can accommodate this type of shape. So hopefully that makes sense. I know we've covered a lot of stuff here at a sort of high level of abstraction, but does anybody have any questions about any of this stuff or specific, examples that you'd like to walk through?
So we lose what the features were in the first place, like because you're trying to capture the distance between data points, so you lose what the features like height, weight, or length or anything was there, but you just have how much the data points correlate with each other. So what's the benefit over there then?
Yeah, great question. So what this does do is it allows you to go from, let's say, like a 15-dimensional problem down to a 2-dimensional problem. In other words, it allows you to essentially visualize really high-dimensional correlations. So that's great. It's good for visualization. It lets you answer questions of the form, like if I went to you and said, hey, Saeem, I want you to look at this data set of athletes. And yeah, I know it's 15-dimensional, but I want you to show me visually some clusters of athletes. Are there clusters in our data set? And then from there you can go, well, let me take a look. I'll run t-SNE, and I know that I'll capture any weird, funny nonlinearities, and it'll give me a really good sense of whether I actually have clusters in my data set, even in that high dimension. That's basically it, though, because I can't even tell you what those axes mean. The axes on a t-SNE plot are meaningless. Like you said, there's no mathematical expression for them even. So they're not interpretable. But they just qualitatively tell you, okay, do I have, are there clusters within my data set, essentially? Does that make sense?
Yep. So I think clusters would be the best example to say that t-SNE is best able to figure out clusters in your data points. Yep.
Yeah, that's right. t-SNE is really good for that. And so PCA is nice because you can actually after you have the output of your PCA process, you can then take those points and do machine learning on them. So you can say, all right, I'm going to reduce the dimensionality of my points down to whatever dimensions, and I can then feed those points into a machine learning model. But because t-SNE, the axes don't mean anything, you actually can't do that. So anyway, PCA, you can use it to reduce the dimensionality of your data set as a precursor to machine learning. So it can be a pre-processing step in addition to a visualization tool. And that's sort of the trade-offs between the two. So t-SNE, great for visualization, more robust. PCA, helpful for downstream applications as well.
I have a question.
Yeah.
So if one of the few purposes of PCA/t-SNE is to kind of see the clusters that exist in your data on an easy kind of 2D scale, why wouldn't you just opt for something like hierarchical clustering and then talk about those more sort of unsupervised clusters that exist in your data?
Yeah, so hierarchical clustering is a valid option. It's another way to go. If you guys are sort of unfamiliar with hierarchical clustering, you can check out, I think we did an office hour session on that. It is a good way to go. The advantages of t-SNE would be that it'll tend to do a better job at capturing complex nonlinearities. Certainly if you want to use PCA for like feature engineering purposes, which is essentially what it is, if you use your dimensionality reduction to define these new weird features that then compress most of the information in your data set, that most of the information in your data set is compressed into, then it has more value downstream than hierarchical clustering because it's a feature engineering thing. I would say that they're to be used in a complementary way. Hierarchical clustering gives you a richer kind of analysis that you can do. There's no doubt, and it can be more useful, but it's also computationally expensive too. That's one of the things to keep in mind about it. All these techniques are to some degree, but yeah, I mean, I would regard it as complementary. It's another way to visualize your data.
Okay, got it. And I have one more follow-up question that is not exactly related. But if we were to use PCA on, say, like a data set that was 5 dimensions originally before we do any sort of reduction. So we're going from 5 down to 4, then 4 down to 3. So reducing, and then again from 3 to 2 so we can visualize it well. So with 3 reductions, does that mean that each axis of what I'm plotting will effectively have like 3 coefficients kind of for the 3 kind of dimensions that I've reduced down to? Would I say like my x-axis is 0.4 of the my fifth feature and 0.2 of my fourth feature and 0.7 of my third feature, and the y-axis is something else?
Okay, yeah, great question. So they're actually all gonna be a mix of all of your features, of all 5 features. And so the way you can see that, at least going from 2 dimensions down to 1 dimension. So yeah, this example I think is pretty useful. So PCA, you can kind of see like, okay, it's a height and weight here. We're going to reduce it down to 1 dimension. This one here, and this would be principal component 1. This would be principal component 2. And you can see that both of these principal components, 1 and 2, they're both a mix of the 2 original features. And the same would be true in higher dimensions. If whatever that plane is, the equation for that plane is now going to be a function of height, weight, and like arm span, or whatever the third dimension is.
Okay, got it. Yeah, that makes sense and is working its way through my brain.
Yeah, no worries. Yeah, Sayim, yeah, go ahead.
I just wanted to say, when you're moving the mouse, kindly keep it slow so that we can see it.
Oh, sorry, yeah. Absolutely. Sorry about that. Yeah, I'm going to have to work my mouse muscle memory. Any other questions? Okay. Well, maybe you'll park that there. So the recording will be up. You'll be able to check it out and sort of like go over this again if that helps. Feel free to send me a message as well. My main hope in doing this was kind of to give a little bit of an unorthodox perspective on these dimensionality reduction techniques. I think it could have been a bit clearer, so I'll think about that and try to iterate on it for next time. But at a high level, hand waving is always good, and think about how you could explain this during interviews as well. It never hurts to go in with like a prop or a book or something. But anyway, I guess that's it for me.
Can I get in one more question before we all peace out?
Oh yeah.
Okay, cool.
Absolutely.
So, so if this is mostly for visualization, then most of the time we're going to want to reduce down to 2 dimensions.
Yeah. Or 3, but yeah, mostly 2.
Or 3. Yeah. Okay. So when you're so let's say you're using PCA not necessarily for visualization, but to then feed into some machine learning algorithm. How would you determine how far to reduce the dimensionality before you fed it in?
Yeah. Okay, great. So this is, I love questions like this because I think they expose one of the dark secrets of the so-called data science life cycle. And this is just the fact that there's no difference that there's a continuum between feature engineering, feature selection, modeling, and data exploration. And so the way you would do what you're doing, what you're describing in practice is you would start with reducing it down to 10 dimensions, let's say, if you were using it for modeling. So reduce it down to 10 dimensions, see what your model's performance is like under that condition, and if it seems to be as good as it was at 15 dimensions, you say, great, no problem. Like, that's perfect. Looks like I didn't sacrifice all that much by losing those 5 dimensions. And maybe get greedy and try again. And you'll decide what your threshold is, what accuracy or F1 score or whatever it is, drop you're willing to accommodate based on, to sacrifice those dimensions. And that's going to be different from problem to problem. But the fundamental answer is you're going to end up treating the output dimensionality as like a hyperparameter in your training process. So, is it hyperparameter tuning? Is it feature engineering? Is it feature selection? It's a bit of everything.
Okay.
I hope that made sense.
Yeah, it did. And I have like a follow-up forming. Now, is the only reason that you would reduce dimensions before feeding into a model to reduce the storage space of your data in a pipeline, or is there some other reason that you would do that?
Yeah, so I actually provide a list of reasons in, I think it's the feature selection office hour maybe, but the upshot is there are a couple of reasons. So first off, you want to limit overfitting, the risk of overfitting, right? So reducing dimensionality is really helpful for just removing the risk of overfitting. You want to reduce the compute time that's required to actually chug through all those dimensions, because every time you add another dimension to your data set, you're not just you increase very non-linearly the number of different feature interactions that now you have to track, right? So if I go from 2 to 3 dimensions, like with 2 dimensions, I need to track 1 interaction, right? But now when I move to 3 dimensions, there are 6 interactions. I can look at the interaction of, 3 interactions, my bad. I could look at 1 and 2, I could look at 1 and 3, and I could look at 2 and 3, right? And so there's that nonlinear increase every time you add a new dimension, and it really explodes on you quite quickly. And so reducing your dimensionality using something like PCA can be a good strategy for that reason.
Thank you so much. That's exactly what I needed, was to connect it to the last office hours you held.
Oh, good. Okay, excellent. All right. Actually, maybe I should make a point of, because it really is, it's a feature selection, again, and feature engineering technique. Because it's not just that you're picking one column and saying, all right, I'm going to use that column, the other ones are useless or whatever. It's that you're saying, no, I'm going to use these principal components, which are like each a mixture of different columns. So you're doing feature engineering and you're doing feature selection at the same time. So yeah, the PCA is a weird way to do this.
Yeah, I totally got it. Thank you.
No problem. All right. Well, yeah, thanks a lot, everyone. Do send me your follow-ups. Again, I feel like this could have been clearer, so I'm going to iterate on this for next time. But let me know if you have follow-up questions as always, and look forward to connecting with you guys on Slack.
Where can I see the video for the last office hours?
On
The
feature
feature?
selection? I'll
Yeah.
post it actually as a comment in the office hours channel right after this, actually.
Thank you very much.
No problem. All right.
Okay, thank
Have a
you.
good one, guys.
Have a good one.
Thank you.
Thanks, Jeremy.
Cheers.
Yeah.
Thank you. Bye-bye.